afternoon. The Atoms Group is pleased to have with us Professor Alberto Striolo. Professor Alberto Striolo is a chemical engineer by training. He received his PhD in chemical engineering in 2002 from the University of Padova, Italy. He also conducted his graduation studies under the supervision of Professor Alberto Bertucco in Padova and Professor John Prausnitz at the University of California. After his postdoctoral research in 2005, he joined the University of Oklahoma as an assistant professor in the School of Chemical, Biological, and Materials Engineering. Tenured and promoted to associate professor, he spent sabbaticals at Princeton University and at Lawrence Berkeley National Laboratory. In 2013, he joined University College London, where he is a professor of molecular thermodynamics. Professor Striolo is author or co-author of over 106 peer-reviewed journal articles, and he coordinates the Horizon 2020 Consortium Science for Clean Energy. Professor Striolo was elected Fellow of the Royal Society of Chemistry, Fellow of the Institute of Physics, and Fellow of the ICHME. So welcome, Professor Striolo. Thank you, and I'll have the word.
Thank you very much for this kind introduction, and thanks for the invitation. And very importantly, thank you everybody for finding time to be here today. It is impressive that we are connecting UK, US, Canada, Brazil, and most likely other countries in this COVID situation. So, yeah, thank you very much. It's a pleasure to be here, and I hope I will be able to give you a little bit of an overview of what it is that we are doing in my group. So I changed the title a little bit, and because I will focus on fluids, but the purpose is to show a little bit about multi-scale. But before we go into research a little bit, I figured that I should introduce a little bit University College London. So here is a very nice picture from the evening, and we are very proud. The QS World Ranking treats us very well, and the Chemical Engineering Department, for the first time ever, has been placed on the 18th in this specific ranking. So we are pretty happy about what the world thinks about us. What we are also proud is that this University College London, was the first in England that opened up the doors to students of any race, class, or religion. And the motto, the Latin version is there, but basically the idea is to let students to come to university only based on their merit and not on any other characterization. So we're pretty proud of where we are. The university is pretty large, 40,000 students, 40,000 academic and researchers. So that's where we are. But I am particularly proud of the group. So this is my group over the years, including the people who have already graduated. Recent graduated people include Abir Kedr and Trang, that are still listed in the group members, but they should be moved into the graduated people. The group is, relatively modest in size, but very good in terms of achievements, I think. And today I will be talking about the work that Trang, Ang, and Sakiru have been conducted, and also a little bit from Dian work in recent free dynamics adventures that we are entertaining. As you know, we are a computational group, so we are very grateful for support and access to supercomputing facilities. And we are also very grateful to collaborations that extend from experimental groups to groups that bring to our arsenal things that we don't use usually. So at the moment, we are collaborating with Caroline Ko in the area of hydrates. Mikhail Stamatakis will talk a little bit about what he does. He does a lot of kinetic Monte Carlo applications. And David Cole from Ohio State University is a very long-term collaborator of ours. So here we are. To put the work into perspective, I'm finding myself more and more engaged with the energy industry. And as we all know, at the moment, there is a significant question on this industry. There are many demands. The society wants this industry to become more sustainable. There are costs that are significant. And for this specific industry to stay solvent, it probably needs to become agile and it needs to demonstrate that it is able to reduce the environmental impact. So to some extent, in my mind, there is the need of this industry to become circular, in the sense that every single aspect, from the extraction of the resources and the energy from the ground, all the way to transporting it, treating it, manufacturing new problem, coming up with new uses to make the whole society more sustainable, and eventually obtain the carbon, reuse it if possible, and store it for many years. The whole thing needs to be integrated, and it has to be to become sustainable. So these activities need to be connected with each other. And today I will mostly talking about transport, really, but in principle, all of these things need to be connected with each other. So today we basically focus on transport on very complex media. So the direct application will be the shale oil and gas. Enhanced oil recovery is to some extent connected to this, and eventually also the carbon sequestration down on the bottom right. So in all of these activities, what we want to do is to be able to access the entire port network, and we want to be able to extract what we want and leave on the ground what we want to stay there. Of course, it's an enormous challenge. It has a lot of cost involved with it, but if we are able to achieve these goals, we should be able to make the entire society much more sustainable. Now, even more constrained, if you wish, the activities that I will be talking about today have been developed with the goal of predicting the permeability of materials such as shale rocks. So here there are experimental pieces of information that we obtained a couple of years ago, looking at the shale sample. Halliburton provided these samples from a shale formation. We used the chem scan to figure out what type of minerals we have in there. And you can see from this figure that the minerals are quite diverse. The material is very heterogeneous. We used X-ray tomography to figure out where the pores could potentially be. So in this graph, the red images represent regions of low density, so they could be pores. And here you can see that there might be a microfracture that extends all the way horizontally into this material that could have been formed when the rock was extracted from the ground. We used another X-ray machine that allows us to show, to see even more refined properties. And here you might be able to start to see something that goes from left to right. And we think that those may be pores that are present in this specific shale rock. When this rock was used to measure the permeability, what was found, which is very typical, was that the permeability is very low, but in one direction, the vertical here, it can be 1 to 2 orders of magnitude lower than on the other direction. So there is a very heterogeneous anisotropic properties on these specific rocks. So the big question is, if somebody comes here and give me a TM image or an X-ray tomography of one of these rocks, can we somehow predict what will the permeability be on that rock without measuring it? And of course, it's a challenge type of problem. And from the simulation side, what we can do is to address several aspects. We can look at the mineral itself, and we can try to answer questions about wettability. So here, this is a paper that has literally just been accepted from the Journal of Physical Chemistry. The author is Trang, and I think she's on the audience. And essentially what she did was to take a calcite mineral. She put a little bit of water in there, a lot of CO2 at supercritical conditions, and she tried to figure out what is the contact angle. And what she found is that for a given set of force fields, water was extremely wet in this material, and the presence of salt did not affect the results much. When she did the vice versa, she put a droplet of CO2 surrounded by water. What she found was that this CO2 was not touching the calcite surface, consistent with the water wetting property that we predicted, but adding salt brought that little CO2 droplet a little bit closer to the substrate. What that will mean in practical terms, we don't know, but there seemed to be a little bit of an effect of this salt to lead to adhesion of some sort of these CO2 droplets onto the surface. Unfortunately, what we found was that when we change the force field, we have completely different results. So now the question is which one of the two force fields is more realistic? And when we look at the experiments, there is also a very large variation of contact angles that have been reported for this specific system. So we don't really have an answer. But what we found very recently is that when we add additives or impurities, we can change significantly the contact angle. So in this snapshot over here, those little cyan spheres, they represent ethanol that was added to the system. And what was found was that just a little bit of ethanol is able to change the ability for these conditions where water is measurable, if nothing else. So now the question is, can we identify impurities that perhaps could help change the wettability of CO2 and water when we come up with the strategies for CO2 sequestration, for example. All right, so this is an example of a study in which we are looking at a single mineral surface, so not even a pore. When we look at pores, typically in simulation, as you know, we are limited to systems that are very, very small. So in this case, the pore size is of a couple of nanometers. And here what we did was to put hydrocarbons inside. And the mineral in this case, it was a silica. The question was, what happens if we add CO2 to this system over here? And what we found was that the CO2 preferentially adsorbs onto the surface. And by doing that, it pushes the hydrocarbon towards the center of the pore, and it promotes more diffusion of that hydrocarbon. So in the table down here, what we have is the self-diffusion coefficient of the hydrocarbon as a function of the amount of CO2 that is present. So when there is no CO2, the diffusion coefficient is relatively low, but then it goes through a maximum as we increase the amount of CO2, and then eventually it goes down again because now the pore becomes blocked. So we introduced here the term of a molecular lubrication to indicate this mechanism by which the preferential absorption of the CO2 might be able to promote the motion of hydrocarbons in specific formations. We continue this study. We have a number of papers there that because we got interested, and of course you can change the mineral as you wish. So here we have a recent work in which we look at muscovite, silica, magnesia, and we basically did the same trick. We added CO2 or H2S, and we quantified the amount of hydrocarbon that can be removed as a function of the loading of the various gases. So in muscovite, what we found was that H2S was better than CO2 at removing the hydrocarbon from the surface. On silica, we found that CO2 was a little better than H2S. But on this model of magnesium material, neither H2S nor CO2 was particularly good. So what we learn here is that depending on the rock, we may or may not be able to use the acid gases to promote enhanced oil recovery. So it's important to understand these preferential adsorptions. Now, of course, many people are skeptical of simulations, so we need to try to see if we believe the results. So this is where the collaboration with Dave Cole became essential. Seeing that we've conducted simulations on silica materials, what I did was to pick up controlled pore glasses. The reason is that these materials are made out of silica, amorphous rather than crystalline, but silica. And what they did, they put ethane in there, and they computed, they measured, the self-diffusion coefficient using neutron scattering. And what you see there is that when you have the ethane in the bulk, depending on the pressure, the diffusion is much larger compared to the ethane when it is confined in this porous material, as expected because of confinement. More importantly, when you have the confined ethane, it's down here, and you compare the bulk, when you compare the mixture in confinement versus the pure confined system, you have a change in the diffusion coefficient as a function of temperature that suggests that the activation energy changes. So these full points, let's see if I can use a pen. These full points over here are the results for the confined pure ethane, whereas these empty points over here are the results for the confined ethane in the presence of CO2. So what happened was that adding the CO2 was able to change the slope of this self-diffusion coefficient as a function of 1 over the temperature. So it indicates that the activation energy decreased because of the presence of the CO2. The absolute values are different compared to what we predicted from the simulations, but the magnitude, the change in this activation energy was consistent with what was predicted by our simulations. So we were pretty confident that perhaps the CO2 was indeed providing molecular lubrication to this specific system. Then the next thing that I wanted to bring up are these systems over here that Anne has been working on. So they're still single pores, but now they're much more complex. And the reason is that she's filling them with benzene. And the idea is to make a pore that instead of being regular, it has a lot of aspericities inside, and it could be representative of maybe a kerogen or something like that. And what she did was to use non-equilibrium in this case, molecular dynamics, and she looked at the transport of methane through these pores, but specifically at the effect of adding CO2 or H2S to these systems. So in short, what she found was that the CO2 and the H2S effectively open up pores, and they allow the methane to go faster through these materials. And that's why there is a little bit of a bicycle over here, because there was evidence that the transport of the CO2 was taking the methane along for a ride inside of these pores. So we thought that that was particularly useful, and perhaps suggesting that using these acid gases could help extracting more of the hydrocarbons from the formations. Now, all of this is in single pores, simple, complex, but they are single. So if we want to start predicting things for large porous networks, we need to somehow build complexity into the system. So what I will do now, I will give you like to do. She basically did a brute force non-equilibrium molecular dynamics, in which case she built pore networks, relatively simple, in which she made pure methane go through. So here we got methane at high density, here we got methane at low density, and she looks at how the methane goes through these systems. At steady states, this is what the density looks like, so she can come up with the fluxes as a function of pore properties. And she really went into the details of setting up different pore structures, represented over here, and quantifying the permeability of methane through these systems. And in general, she tried to keep the porosity constant, but change the distribution of small pores versus relatively larger pores. And then she tried to come up with models to relate this permeability to properties of the pore networks that include the permeability, the constriction, and the porosity of these systems. So now what we think is that we have an equation down there that could be used to look at the material, extract these quantities from experiments, and then predict what the permeability will look like. So that's one way in which basically we are doing a brute force upscale from a single pore to multiple pores. But of course, we have very few. The next thing is to connect and to use the molecular to provide the boundaries for lattice and so lattice boson. And this is what we did together with Dian. And these are the results from the MD that Anne conducted. And the results are for both the density and the velocity of the methane in various locations. And then we use that velocity near the surface as an input for the lattice Boltzmann simulations. When we are happy with a boundary condition, then we can simulate the transport of gases in relatively large systems, such as those that are represented here. And now what he was able to show was that using the boundary condition that he gets, we have results that are consistent with what is reported in the literature, but much closer to the experiments compared to what other lattice Boltzmann simulations have reported. And the reason is that we think that the the boundary condition that we came up with is a little bit more physically consistent, and it allows us to capture the complexity of these systems. That's the second way in which we are using the MD as an information for the lattice-Boltzmann simulations. The third approach, well, this may be a skip for now, since we are running out of time. Basically, we're looking at particles transport inside of the pore networks. But the third approach was to use a stochastic analysis. And the reason is the following. Even with the lattice-Boltzmann, we are only able to look at relatively small pore networks when they are compared to realistic samples of rocks. We do know that many rocks are very, very heterogeneous. So how can we predict the properties of a rock if we are only looking at 1 centimeter cube of that specific rock? And in this case, what we're doing is this kinetic Monte Carlo approach. So in short, we take a SEM image of a shale formation where we can see that there are dark spots and there are lighter spots. And we say, okay, the white spot may represent the clay, the dark spot may represent the kerogen. So we digitize this image and we get some average properties of it. Like, for example, the connectivity of the dark spots, how big they are. And then what we do, we generate maybe 100 of similar structures like this one that have the same features, the same connectivity of the dark spots, the same distribution of their sizes. And then for each of them, we assign values of permeability that will be representative of the permeability of the clay versus the permeability of the kerogen. And then for those 100, we use this stochastic approach, the kinetic Monte Carlo, to predict what the permeability will be. Then we average the 100, and we now have a prediction of what will be the permeability of a rock whose properties are statistically represented by this SEM image. Does it work? Well, first of all, does the KMC approach work? So here we demonstrated that for one-dimensional pores, it is able to reproduce quantitatively non-equilibrium molecular dynamics simulations. So here, Anne conducted transport of methane through a pore that was filled with water. She found that there is a resistance for the methane to go in, there is a resistance to diffusion, and eventually the methane goes out. So then we can reconstruct a one-dimensional system that is very simple. We got the bulk here, we got the interface over here, and here we got a pore. We assign a diffusion here, a barrier here, and the bulk diffusion over here. And using the information from the MD, we are able to now upscale and predict the flux as a function of pore lengths, pore connectivities, etc. So that it's very good, and it allows us to look at the effect of pore sizes and pore connectivities in one dimension. Then in 2 dimensions, we can do similar things, but now we can distribute pores with high permeability and low permeability in different locations within a 2-dimensional material. And we can now quantify the effect of anisotropic properties. And then what she did, this is Maria, what she did was to look at the diffusion from molecular dynamics as a function of pore width. And she found that 4 or 5 different chemical materials of the pore. And what she found was that after 3.5 nanometers, we always recover bulk diffusion. But for shorter pore widths, we are able to have a strong effect of pore confinement on the diffusion. Now, this allows us to have a library of diffusion properties as a function of pore widths. And now what she can do is to build up 3-dimensional structures in which, by knowing what is the pore size distribution, the chemistry, the connectivity, we are able to spit out predictions for the permeability of those rocks. That paper is still under review. I hope it will be soon accepted, but we'll see what happens. But in the meantime, in the 2-dimensional version, experimental permeabilities are in this range. And what we have been able to predict with our KMC approach is basically right in the middle, simply by looking at a TM image of that structure. For completeness, it should be pointed out that even these 2 analytical approaches, the effective medium theory and the simplifier renormalization, they give values that are consistent with the experiments. But in this specific case, everything is consistent because this image is very isotropic. If we were to start using materials that are not isotropic, the kinetic Monte Carlo will have significant advantages compared to the effective medium theory, for example. So that's the third of the approaches, and which in 3 dimension now allows us to look at the effect of connectivity, porosity, pore throat, and so on and so forth. So bring to the conclusion, essentially now what we think is that with this multi-scale approach, if somebody gives us the properties of a rock, of a shale rock, we should be able to conduct a few simulations to adapt our models, and then we should be able to predict what the permeability will be. Now, to go back to the initial vision of this circular energy industry, we have only discussed this part over here with connection of the storage over here. If we want to go all the way to the manufacture of chemicals, there we have a lot of catalysts. And for applying these techniques to the catalyst, what we need is to room to go, but I think the modeling as a good opportunity over here to be able to say that they will have a lower environmental impact compared to what we are used to from that industry. Now, to conclude, I started by giving you a little bit of an overview of UCL, University College London. I want to show you a couple of people that came to school here. So this is a band called Play. They were famous when I was a postdoc. Now probably the younger generation are not familiar with them anymore. But anyways, they were students at UCL. Christopher Nolan was also a student at UCL, as a famous film director. Gandhi was a student. And this here is Jeremy Bentham. He was the founding father, so to speak, of UCL. And his mommy, this is his real mommy, is conserved very close to our cafeteria. So whenever we go to eat, whenever we are on campus, now it doesn't happen very frequently, we need to go across him, pay our respects, and then we have access to the food. This actually is head, mummified head, and it is not displayed all the time. It was shown only for a short period of time during the time that I was at UCL. So with this, I bring up the picture of the group over the years, and I should probably stop and see if there is time to address questions, if there are questions.
Thank you.
Thank you, Professor Striolo, for the interesting presentation. We are now open for questions. If you want to ask one, please enable your microphones. And of course, your YouTube views can write it down also. So any questions?
Yes. I wonder, can you comment something about the comparison that you can think about Lattice-Boltzmann on kinetic Monte Carlo? Because I think it's, well, for me, it's straightforward to use Lattice-Boltzmann instead of kinetic Monte Carlo, due to you can have better time scale information, and you can use a lot of wettability and a lot of information in Lattice-Boltzmann. So can you comment about this?
So we are beginning to use the Lattice-Boltzmann. It is very powerful, no doubt about that. And as you mentioned, you can include a lot of information. So far, we have been able to look at pore networks that are relatively extended with very promising results. So far, we have only looked at single-phase fluids, but as you mentioned, you can look at different fluids. And we are now using it to look at the transport of particles, for example, tracers, in the formations. So it is very powerful. The one thing that I think is limiting it is that you need a representation of the pore network that is, relatively extended. and to be able to capture all the physics in it. For example, now that you're looking at this particles transport, we are rapidly approaching what we can do on a single computer in terms of size of the system before we need at which we can believe the results. So there are some issues there to make a direct comparison to the experiments. The kinetic Monte Carlo, on the other hand, still has the issue of the size, because when the system is too small, you cannot believe it. But it allows very fast calculations. So those predictions of permeability in 3 dimensions, they were done in a few minutes, multiple representations, and we can produce many pore networks that have similar features and average the results out. Now, what you need there is a very realistic description of what the fluids will be doing in the different locations within the pore. So there is a lot of bookkeeping in kinetic Monte Carlo, but in principle, it allows you to go to bigger systems and to get better statistical averages. The lattice Boltzmann is very deterministic. You can actually see what is happening to your fluid as it moves. So it has, they both have advantages.
Thank you. Just to complement, in a time scale of molecular dynamics, we are start to use here DFT, dynamic DFT. Have you ever tried this?
I have not.
It's for short time scale.
Yeah. I would ask that question to Walter if he's still online there. I've never used the DFT. So I don't. I've seen very impressive results. It's very convincing. If I remember right, those results tend to be on a single pore, but they are very impressive. But I've never used it, so I don't know.
Thank you, sir.
May I ask one?
Yes, please, Bruno.
Very nice talk. I would like to know that in the beginning of your talk, you mentioned about some force fields that were giving different results. And I was curious to know what are the force fields that you are working with?
So you are referring to the liters one slide that I had for the calcite water CO2 system. So funny enough, what we recently found is Tran, she's on the call as well. She told me yesterday was that she was using the flexible model for the CO2 and a typical SPC model for water, or the TIP4P 2005. So for that combination, if you put an hydrocarbon in there, that hydrocarbon ends up being soluble in the CO2 just because of the flexibility. If you use the rigid version of the CO2, that hydrocarbon is no longer soluble in that CO2. So that's a very funny thing that we are still exploring. However, I was referring to the models that we use to describe the solid water and the solid CO2 interactions. The first author is Xiao, that developed a force field to describe those interactions, and that seems to be, well, they're both good as far as I can tell, but the Xiao force field predicts very wetted calcite surface. And there is another force field that was introduced a couple of years ago. Now I can't remember the first author of that. And in that case, water is actually beating up on top of that calcite substrate. The disadvantage of the second force field is that it does not allow you to describe electrolytes. But there has been a recent development in which because it's using an exponential 6 interaction rather than a Lennard-Jones description. Recent developments have introduced the Lennard-Jones version of it, So now it becomes very, very comparable to the Xiao force field. What we have recently done is just to say, okay, the contact angle is different, but what about other properties? So a paper that we have not submitted yet, we are looking at the water layering on top of calcite as predicted by the two force fields, and they are basically not distinguishable, and they're very much consistent with the XPS type of experiments. The only difference is that the residence time predicted on top of the calcite is quite different from the two force fields, but that is a quantity that is very difficult to get from experiments. So the jury is still out to figure out which one out of these two is more reliable.
Very nice, thank you. I have just one more quick question about the work of N, the simulation of non-equilibrium molecular dynamics on the pore.
Yeah.
If I understood well, you apply like an acceleration field to the system.
So
when you want to enhance the.
So here, in this little area, wherever the molecules are sitting in this volume, they are given an acceleration.
Okay, I see. Okay, thank you.
And then they just. So at the beginning, everything is uniform, then there is a transient period, and then eventually you find steady state conditions.
Okay, I understood. Thank you.
Hi, Alberto. This is Charlie from U of A.
How are you?
How are you?
Hi, Charlie.
So, hi, Federico. How are you?
Not bad.
I just have one quick question here. So, just looking at these slides, I understand that, Alberto, you use you focused on the pore size, but sometimes I noticed that the length of your pore is only around like 10 nanometers. But there was a report in around 2008. People say that the length of this nanopore would also affect the flow because effectively you have two pore ends, and if they are too close, they would affect each other. Could you comment on such effect on your diffusion or flow in the simulations, please?
So here, this is absolutely right. When you have a flow, the pore entrance and the pore exit are the important limits, and then you got a somewhat uniform diffusion in the middle. So here is the results that we got here out of this kinetic Monte Carlo approach. So we tuned the approach to make sure that we are able to reproduce the molecular dynamics results, and then we are able to predict the effect of pore length on the flux, so the diffusion. And what you see is that it keeps going down as the pore length increases because of the combination of these factors. So it's definitely important. It is one of the factors that need to be taken into consideration. Now, how long does it need to be to get the reliable data? It depends on what material you're trying to reproduce. Usually the free energy barriers, they are, I would suspect, a couple nanometers. That's where they stop, and then you start having pore-like behavior in the middle. We have different expectations.
Can I ask a follow-up?
Okay, thanks.
Thank you.
Could I ask a follow-up about that same issue?
Yeah, go on, Richard.
Hi, Alberto. Nice talk. Good to hear from you. So we actually studied a similar system. It was much more controlled, really. It was silica light, and we used dual control volume GCMD, and so it was a non-equilibrium molecular dynamics method, and what we saw was a lot depended on the ratio of the size of the molecule to the size of the pore, and the way we explored this was if you think about it as a series of resistances, then you basically plot, I think it's 1 over the flux, and then the length of the pore basically goes in the numerator. So then, you know, the flux goes down as the pore gets longer, but then since the surface resistances are constant, what you can see then is as you make the pore longer, you can back out the surface resistance as the constant of the regression, right? As the intercept.
Yeah.
And so what we saw was that the magnitude of the surface resistance was significant relative to the pore length resistance, even out to like 100 nanometers, I think. And that was just with methane. If you talked about perfluoromethane, which is a pretty much bigger molecule, then it went out to like 200 or 300 nanometers before you could actually say, oh, the surface resistance is negligible relative to the pore resistance.
Now you scare me. So now I see that it's Richard. So hi, Richard. I didn't recognize it.
Hi.
So in this work over here, we did that as well. So at some point, we said, okay, let's keep the pore length the same, but now let's break it apart. So we have different barriers, and we are being able to quantify the fluxes as a function of these. Now, in our study, the resistances are an input, and I completely agree, right? The pore entrance is the dominant resistance in this specific system, which is more, what can I say? What's the right word for it? You would expect this to be the case here because the pores are actually filled with water. So the methane has to get into the water before it's able to move, and then it gets to get out of the water, and then it gets to get back into the water again before entering the next pore. So I completely agree that the pore entrance can be very significant. We did not quantify the resistances to figure out at what point it becomes minimal. And for these KMC approaches, it is doable to describe, okay, that the methane is going from a bulk system to a pore system, and it needs to go through a resistance. And we put that in terms of a barrier that methane has to jump. We did not quantify how long it takes for that resistance to become negligible. But it's interesting that you find such very long pores.
Right. It was quite surprising to us. We started off with the assumption it wasn't going to be important, and then but basically we tested it by making that plot that I talked about, and Martin and Siepman, Ilya Siepman, had done some early work on that exact system, and when we plotted their data in this 1 over flux coordinate space, then the surface resistance was evident in their data also, and it was pretty close to the same value we were observing for the same system.
Interesting. So,
yeah,
if you apply that to a real system, what it means is that the pore entrances become the dominant effect in most cases.
Right, and David Scholl, in full disclosure, I should say that David Scholl had some argument that he didn't really believe this thing, but he never actually showed me a plot of 1 over flux versus pore length, and just show me what intercept did he get, and so I never really understood what his argument was. It sounded like a lot of words, but not a lot of look at the data and here's the intercept and here's the slope.
I would expect that the pore entrance is important. But I think it's also consistent with David's very early work when they were looking at carbon nanotubes, right?
Right, and so yeah, carbon. I think this was right around the time, or shortly before the time that he shifted his attention to the carbon nanotubes. It was a JPhys Chem series of papers that we wrote, maybe 2004, somewhere around there.
No, we'll check them out then. Let's see what, because you know, in many systems these pores can be very short, so it may end up being. Maybe we spend a lot of time to figure out what happens inside of the pore, whereas we should be looking at the entrances.
Yeah. So are you saying that the experimentally the pores are just that short?
They can be.
I see.
These relatively short things. They keep, you know, they get short and they become big, they become short again.
What are we looking at there? I can't understand it.
This one is a shale sample, and this one is a 3D tomograph in X-ray. So this one is 800 microns, and this basically any one of these red spheres represent a low density area, which could be a pore or could be a kerogen inclusion. And this one here is an image of the same sample, but with a different X-ray machine. And now this, I can't really see what the number is. It's 60 microns. So, and these ones here, they probably are the pores inside of the clay matrix. So, you know, yes, they're long in the nanometer length scale, but when you're referring to hundreds nanometers, they become comparable.
What's the pore diameter, roughly?
For this one, that's the information that we did not get into. But the pore size, I should have them somewhere. It may take a while to find it. Oh, here they are. These are pore size polydispersities that have been measured in shell samples. So the diameter is on the order of, for this part, the organic matter, on the order of 20 nanometers, and these ones, a few nanometers to 20 nanometers.
Okay, those are much larger pores than what we were dealing with.
These ones, yes, but these ones, no.
You know, ours were like less than 1 nanometer pores in silica light.
All right, what we're looking at is usually a couple nanometers.
Yeah, yeah. So it might be a less of an effect for those large pores.
Well, yeah, at some point, but at some point also the resistance inside of the pore will become, if the pore is very, very small, it becomes comparable to the size of the molecule. There will be resistance.
Yeah, that's when you see the effect.
Let's move for other questions.
Just a quick question about the pore length. If you are to simulate a long pore, as Richard said, such a long pore, then most of the atoms in the simulation box becomes atoms of the pore of the solid. That is not so interesting because they don't have degrees of freedom. Basically, they are just there to impose a potential. Do you consider such simulations with a simplified model of the solid material?
I don't go to a very, very long pores, but there are simplified models for the surfaces. They will be relevant for crystalline type materials. The roughness of the pore can be important.
Yeah, you can decorate the surface of the pore with a atomistic model. Maybe you can combine both.
Here in this work here was done amorphous materials. But what I found was, depending on the composition of the system, you're able to swell the benzene or to contract the benzene, and sometimes you're able to get preferential pathways. Now, in that system over here, the preferential pathway was never on the surface, but it's possible that in some cases you have preferential pathways on the surface.
I see.
Yeah, that's where one has to make a decision. Do I want to look at the atomistic precision with everything, or do I simplify things? Do I use the molecular dynamics, or do I move up to the computational fluid dynamics? You try to do the best you can, I guess.
Yeah, sure.
So there's another question from Professor Zhang. Professor Zhang, do you have your microphone? I don't know. She's asking, what is the best spatial and temporal resolutions of the X-ray tomography?
I wish I knew the answer on top of my head. I will have to come back to that later. Yeah, not my area of strength, I'm afraid.
Okay. To ask a question here. Reza, you're telling me you have a question. Do you have your microphone to ask the question? If you so, you can go on.
Yes. Hello? You can listen me?
I can hear you, but it's very, very low. Can you speak louder?
Okay, thank you. Thank you, Professor Alberto, for your interesting presentation. I'm Reza. As you know, carbonate rocks have a positive surface and usually are oil wet. You have mentioned that you use water and NaCl brine and ethanol for wetting rocks and changing wettability. Please explain more about it and how you derive your permeability formula in your modeling. Thank you.
So for the carbonates, we have recently started working on them, and so far we have not put any hydrocarbon on them. We're beginning to see what should happen. They should be oil wet. That's what we would expect, but they also seem to be very hydrophilic, especially these ones. So we need to figure out what are the drivers, what are the physical conditions here. We did a little bit of preliminary simulation with the hydrocarbons, but the model for the CO2 was not really helping there because it was solubilizing the hydrocarbons. So now that we have figured that one out, we should be able to observe what is going on there. We put ethanol just out of curiosity to see what could happen. Can modify that contact angle. Does that answer your first question?
Yes, thank you.
All right.
And please tell me about your permeability, your form.
So for the permeability.
Could you understand, Striolo?
Yeah, I think so.
Okay.
He's asking how do we predict permeabilities?
Okay.
So for the permeabilities, here we are essentially looking at the flux at various conditions, and then from the flux we reconstruct the permeability. In one paper, I can't remember which one it is, we reconstructed the relation between diffusion coefficient and permeability. But in general, what we do, especially in this other work at the end, the three-dimensional, what we are assuming is that the diffusivity becomes a measure of the permeability. So we just look at what will be the diffusion here, and we say, okay, the permeability must be proportional. So here, I didn't point out, but the one thing I like about this that has not been published yet, waiting to hear what happens, is that we created the three-dimensional version of these 4 networks. And you, Fred, asked what's the advantage of the kinetic Monte Carlo. So we have these 3D versions, and now we cut two-dimensional slices through them, assuming that instead of having a rock, we now have only TM images of the rocks. And we are like, all right, can we predict the permeability using those two-dimensional representations? And what we found was that here we have 5 different slices, and we predict the permeability into this. So you see that we have very large variations. The average is this one over here. When we do the average of the 3-dimensional versions, we are here. So in this specific case, it's not that different, but the porosity was only 5%. When we go to systems with larger porosity, we have, these are the 2-dimensional variation. These are 2-dimensional representations. This is the average that we get from those. But in 3D, we have something that is 3 times larger. So when we have significant porosity, we can have very strong deviations from the permeability that we expect looking at the 2-dimensional version versus when we have a 3-dimensional porous. And the reason is that the 2-dimensional renditions, they may not be able to see the connectivity between the pores.
Exactly. It's expected, right?
It's expected, but we are able to quantify it.
Mm-hmm.
And to me, it's also surprised that the 5%, it actually doesn't make a big difference. So in some ranges, the difference is large, but in others, it's not. And the reason is that in 5% porosity, the diffusion, the permeability is so low that it doesn't really matter what you're looking at. It's just low.
Mm-hmm.
So, to do this quickly, I think a stochastic approach is advantageous compared to setting up a number of systems for a fluid dynamics analysis. Now, that said, to go back to Richard's question, here we are not looking at the resistances. We are just assuming once the gas goes here, it becomes pore. But that can be included with a little bit of bookkeeping activities.
Nice.
Okay, so it's getting late. Maybe is there anyone has a last question before we wrap it up? Okay, I think we're done. Let us thank again Professor Striolo for the great presentation. Thank you.